My name is Tao Hong. I'm one of the directors of International Institute of Forecasters. Today, we are honored to have Professor Rafael Warren teaching this IIF Distinguished Lecture on electricity price forecasting. Today is day one of a two-day series. In total, we'll be having 4 lectures, 2 on each day, and about 1 hour per lecture. Professor Warren is well known for his work in electricity price forecasting, and for myself, I read his book when I grew up. So before I entered this field, I read his book in load and price forecasting, and later on, I read his papers in price forecasting. So many highly cited papers. All of my students read his papers. We hope as an institute, we can archive this knowledge and broadcast it to the broader audience. Eventually, this will be uploaded to YouTube, IIF YouTube channel, so you'll be able to see it over there as well. Okay, so today is the in-person lecture, today and tomorrow, for Professor Warren to teach this content to you guys, right here at UNC Charlotte. Okay. Yeah.
Okay, thank you very much for the introduction, for the invitation. Let's see how this works. I'll hide the camera so I won't disturb you. Okay, this is a screenshot of the web page. If you Google my name, it should be pretty easy to find the web page. And so if you Google my name, go to conferences, select IIF Distinguished Lecture, and then you can slide down. There are both the lecture slides, and these are hyperlinked documents, meaning that most of the things there, some of the graphics, many of the references are hyperlinked with DOI numbers, so you can easily access those papers. This is more or less the contents of tomorrow's lectures, and at the down here you have a GitHub repository with the codes. Mostly in Python, there'll be one snippet in Julia illustrating the concepts that I'll be talking about today and tomorrow. And these were prepared by Agli Piecki, who will explain them to you later today. Okay, so let's go down to business. And let's start the presentation. Okay, this should be fine. Okay. So electricity price forecasting, I mean, this is a pretty broad topic, and I've been in this business for the last 20 years or more. So over the years, no, actually more. I'm a bit older than that, so it's a bit more. But yeah, the community, the methods have evolved over time. So I'll go over different aspects. I'll start from what is electricity price forecasting, what are we really forecasting, then go over the methods, the techniques to evaluate them, and give you, especially tomorrow, some more recent advancements to show how you can implement them yourself. So starting, if you go and search for the literature, well, if you think about energy forecasting, then price forecasting is just one of the sections. Actually, this is the smallest one. It's kind of a niche here. As you can see here, the red bars here represent number of papers which somehow have been classified. I use the same classification as we had in the paper with Tao and colleagues published in 2020. So this is just the updated data. You can see, well, the paper inflation in our areas, but some of them becoming more prominent, especially solar. You can see almost from 0 to really 1,000 papers a year. Some of them from starting like price forecasting, they haven't evolved that much. So the numbers of papers are not that huge, but I'll be talking about a very important area on the interface between engineering and economics or finance. And of course, using a lot of tools from statistics, econometrics, machine learning. So this is the area of electricity price forecasting. If you think about where to look for papers, research articles on electricity price forecasting, then this gives you a list of the top 10 most popular in the sense in the number of energy forecasting papers, journals. And again, it indicates where you can find papers related to a given area or sub-area of energy forecasting. So if you're looking for price forecasting, apparently it's the IIF, International Journal of Forecasting, which is one of the leading journals for price forecasting papers. There's electric power systems research, transactional power systems. There you can find some papers. And on the economic side, it's energy economics. That's more on the economic applications, but I suggest look at least at those four. There's a bunch of papers also in applied energy. So look at into those journals if you want to see what is happening in the academia in this context. So okay, so what are we really forecasting? First, the world has changed over the last 2 or 3 decades, really, coming from, well, the initial reforms were in the 1970s. The big changes started in the mid-1990s, where you had the regulation and the establishment of competitive markets for electricity. Now, the world, this is a nice study if you want to have a look at it. This is also hyperlinked. So if you just hover your cursor over this, you will see the link to the webpage where you can access the data. So based on this data, you can see that a large part of the world is the dark brown, meaning this is the power exchange type model, where you have the producers and the consumers bidding into the market. Another part, North America, especially in Australia, this is a part of the world where you have pool types markets, whereas the generators that bid into the market, you don't have utilities bidding in the market and taking active part in the price establishment. Now, if you look about how the prices are established in both types, so the pool and the power exchange type, as I said, in the pool market, essentially you have bids from which you can construct the supply curve. The demand is an estimated demand by the ISO, by someone who kind of predicts the demand for electricity. Whereas in the power exchange, you have both sides. So you have the demand curve, where you have utilities and buyers, wholesale buyers bidding for electricity, and wholesale sellers. And of course, as in any kind of economic market model, the intersection gives you the volume and the price. So it's always the intersection that gives you this. Now, of course, there's very specific characteristics of electricity prices you observe later is a result of the nonlinear structure of those two curves. So a shift in the lower end, so like if the demand shifted this side, well, there wouldn't be much of a change in the price. Whereas if it shifted by the same amount somewhere here, the price change would be huge. So because of this effect, you see periods of very extreme price changes in this market. That's why initially I became interested in these markets. Why? I mean, with these extreme price fluctuations. Now, you have different types of pricing in those markets. We've heard already today about nodal pricing, which is popular in the US, Canada, New Zealand, where essentially, well, here's a nice illustration from National Grid, one of their publications, where you have a map of Great Britain with some artificially put nodes. These are not actual nodes, but nodal pricing would mean that every major node in the system can have a separate price. Whereas in Europe, actually, we have a different setup. Most countries run on a single national price. So in the UK, in Germany, Poland, we have one price for the whole country. In some countries, especially Scandinavia, but also Italy, we have and also Australia, we have zones. So there are different parts of the country which can have different prices, and the price is established for a given zone. So depending on which market you're working on, you'll be working with different types of data. In Europe, you can also think of different countries as being different zones. So in a sense, we have single national prices, but since they are connected in the bigger system, essentially it's kind of a huge zonal system. In North America, you call them ISOs, the independent system operators, who essentially are in charge of the grid operation, scheduling, and stability of supply, or regional transmission organizations. And you have the primary model is the nodal pricing with a day ahead, at least this is what I checked in the statistics, is roughly 95% of the volume is in the day ahead markets. The real-time markets are much, much smaller. Now, if you look at Europe, we call them transmission system operators, which more or less are similar to ISOs. Typically, there's one transmission TSO in a country, with the exception of Germany, which has 4 TSOs. But we have a number of price coupling mechanisms, which work either on the day-ahead market or the intraday market. And I will show you in the next slides what this means really. I mean, what is the effect of this coupling? And as I said, we have in Europe primarily zonal pricing with zones which can be whole countries like here, Spain, well, Portugal, France, Germany, Poland. And the day-ahead market has still a very large dominant share, but the intraday market is really picking up a volume. And in some countries, for instance, Germany, it has reached 20% of the volume. So really a large share of the market is traded in intraday markets. And now, what was the effect of the establishment of market coupling? So kind of a common order book for the orders coming from the different regions, the zones, the countries in Europe, is that you can have prices which are similar, almost identical in those countries, in different countries. Here's an example of Germany, France, Poland, and Spain. So going back one slide, these are these 4 countries: Spain, France, Germany, Poland, essentially stretching across Europe. So you could expect that there's some link between German-Polish prices, German-French, French-Spanish. Now the effect is that there are some periods where this is 1 week, just over a week ago, essentially, just downloaded it freshly, where you have for the periods where prices are almost identical across Europe. There are periods when you have prices in 2 regions, like for instance here, the red and the orange, which is Poland and Germany, the neighboring countries, they have identical prices, but at the same time, France and Spain have a different prices, but also identical. Or you can have periods like here where every country has a different price. And why do we have this? Essentially out of transmission constraints. So if you want to transmit electricity across Europe, you need the capacity to transmit from one zone to the other. And if there's shortage of it, then you see these different prices. Okay. Now the timelines of these markets are again not identical in every country. They are similar but not identical. Are we talking mostly about day ahead? Because if you look at the literature, it's mostly the day ahead markets which are analyzed, and they're kind of a reference point across the world, except in Australia where it's essentially real time. And we have in most, let's say, European countries, we have bidding until noon or a few minutes before noon. Then there's the price settlement, the bids and the offers are aggregated. We get the market price for each block. I mean, for each load period, which is typically hourly. So this is taking place 1 day before delivery. So around noon, you already know the prices for the whole next day. And then you can start trading in different types of auction markets. Intraday markets. They can be auction markets, but they can be also continuous trading. So this is something which is not very common in electricity markets, but there are markets for where you can trade products, and the products can be a quarter hour, a half hour, or an hour, and it's continuously traded between some hour on day B-1, I mean, shortly until half an hour or a few minutes before delivery on the actual day of delivery. So this is a pretty complex landscape of how the markets look like, and predicting the prices in a given market. When predicting the prices, it's very important to understand what is available when, not to have data leakage. I mean, that's what you call it, when you can use data from the future to predict the price. Now, as I said, the day-ahead market is the main reference point. It is also the main objective of research. If you look into academic literature, mainly papers about day-ahead markets. In the day-ahead markets, typical construction is such that you bid until some hour of the day, around noon typically, then you know the prices for the next day for each of the load periods. With continuous intraday markets, you start trading in the afternoon of day D-1, and then you have continuous trading until some hour, let's say this one, and this is the delivery hour. These are very different products. Here, you are modeling a vector of 24 prices typically. Here, you would be predicting trajectories of prices. Very different objects. We've just heard before about functional data analysis, where you represent the data as functions. So functions and points are different objects. Like here also, we have vectors of prices and a continuous, essentially continuous trading like in typical financial markets. Okay, this means that the models we build have to somehow reflect this structure. Now, this picture, first one is taken from my review, 2014, where we had different classes of models defined. This is more a very recent application for a project we got from the German and Polish Science Foundations, where we have more focus on really on the predictive models, not so much on understanding how the markets work, how agents work in the markets, not so much on pricing the products. So we don't care about reduced form. We essentially look at short and longer term, where we use machine learning models, statistical econometrics are different names for them, and sometimes fundamental, especially if the forecast horizon exceeds a few days. Then you need a bit more information than just what you have in the classical time series models. And potentially combining those different approaches can give you an improvement in the longer term. So this is one of the things we are just studying now. Now, getting back to the day-ahead market, because mostly my talk will be about day-ahead markets, is you can treat the series as a univariate series of hourly granularity. So watch on 1 hour, you have an observation, and you can just think of this as, let's say, some sample prices for a week, and then you make a prediction for some series on day D+1. But most papers would actually treat this as multivariate series, because all these prices on day D+1 are established at the same exact time, essentially noon the day before, using essentially the same information. So it's not that we are trading different, it's not a continuous market. It's more like every day you get at noon, you get a whole vector of 24 prices. So this is a more natural setting, this multivariate setting. Yes, and we can do functional data analysis here, of course. There are very few papers actually, but there are papers where people look at how you can approximate those 24-hour curves by functions and try to model the evolution of those functions in a function space. Mathematically, it's a very nice object. In practice, the results that have been published so far are not really promising. In the sense, you get much better forecasts from models that are not FDA models. You can go a bit more fundamental in the sense you are not only modeling the price itself, but the curves which define the price. So you can model, let's say, the supply and the demand curves. And then, of course, once you get this right, the intersection will give you a price. It's a pretty nice paper from my colleague Florence Hill and co-author. They call it the X model, where they actually, this is what they do. They discretize the curves and try to model the evolution of those prices. There's a more recent paper that goes in the same direction by Shah Alisi. Yeah, this is also possible, but there are very few papers on this kind of models. And it's really hard to get them really to have these models give you predictions which are more accurate than the other models, let's say, statistical machine learning models. But conceptually, there are very interesting models. Okay, so this is section 1. It's a very brief introduction. I know if we need to make a break at this moment. If not, then probably I'll go on, and then after the section, section 2, we make a longer break for questions. the icon here means there'll be some snippet explained by Arek. But for now, let's move on to some toy models. So this will introduce the model classes that are used in some simple terms, and hopefully you get the idea of what kind of models we can do. Now, before we start that, let me make clear that you should, when you're making a prediction, it's very important what you use as your window to train your model, calibrate your model, estimate your model. There are different names which essentially mean the same, although some people see some distinctions between the names. But essentially the model, this is the gray part is where this is the data, the in-sample data on which you train your model. So get it work right. And the red is the out of sample, the test window. Now you can have a fixed calibration window, and then of course make the predictions for all points in the test window. The problem is that when you get to this point, the information here is, I mean, you don't really have up-to-date information. Okay? So an idea would be, for instance, to use all of the information you have. So this is called an expanding window. Sometimes in some papers you can find the name a recursive scheme. And this way, the window expands in time. Every time more information is known, you add it to your model and train your model on a larger data set. Now, the problem with these kind of approaches is that the characteristics of these objects change, and you cannot use some tests which require some kind of a stationary behavior of your models. So a better approach, and this is the one that we've been using in most of probably all our papers, is a rolling window approach, where you have an in-sample period where you train your model, you make the forecast for, here's just one dot, but potentially you can have several horizons. Then you move your window by one observation in this direction. So you forget about this observation here. You have one more recent observation. The length of the window is the same. So in a sense, the stationarity of the process is conserved. And then you make a forecast for the next day and so on. And of course, the length of the rolling window can change. So this is a longer one here, a shorter one here. I'll talk about these windows again, but okay, it's important to know what kind of a setting you're using. I mean, I would recommend in general using this setting, unless you have extremely computational intensive calculations to be made. And for instance, and then in this such a case, you can use this kind of setup, and every once in a while you can recalibrate your model. This is typically done for hyperparameters in large machine learning models, where the hyperparameter space is so huge that doing it every day will be really time-consuming and maybe not feasible for some models. So you do it only once in a while, but then you retrain the weights itself on a daily basis. Okay, for the models I'll be using here, the notation, this is the simpler notation where T is just time here, but quite often in many papers you see that P has double indexing, indicating the day and the hour, kind of to represent that these are vectors of prices. So for day D, you have 24 prices. The forecast will be indicated by a hat here. And typically, in most, unless I say it's something different here, this would be a forecast made on the previous day with the information of the previous day for day D. The prediction error, or sometimes called the residual here, will be the difference between the actual and the prediction. Well, of course, you can define the opposite way. It doesn't really matter, but it's okay. I use this notation here. And now I will go over 5 very simple models that can be used. The first one is just a super simple benchmark. And if your model doesn't beat this one, then you should change your job, essentially. I mean, this is a naive forecast which looks back either on the previous day, and this is true for Tuesday through Wednesday, or a week earlier, and this is true for Monday, Saturday, and Sunday. Of course, the weekend is different. You can expect the weekend, the consumption is different, the business activities are different, and the prices will reflect it. Monday is also different, especially in the morning hours. It's a different day than a Tuesday, whereas the remaining ones are similar. So here you look back 7 days ago. There's no calibration here, no need to estimate any parameters, super simple. You can even have simpler alternatives. Just look at the previous day, the same hour, just the previous day, or the same hour 7 days ago. Well, this one has a problem because if you switch to weekday, weekend, well, you have the big changes, not really great model. This one loses a lot of information. But okay, it can be used for simplicity, just as a very simple benchmark to see whether you can do it or not. Okay, now the main building block is a regression model in electricity, not only in electricity space forecasting, but also in electricity space forecasting. When I say regression, it doesn't mean it has to be a linear regression model. It can be actually a neural network, which can do also I mean, in some form, it is really a regression model. So the predictors can be different variables. So for instance, some of these can be the load forecast, typically, if you want to make a prediction, the renewable generation forecast. But some of them can be the past values of your process, and then you call it autoregressive. So it's you would know this as AR. ARX would be when you have both past values and some exogenous, so a different variable used in your model. The betas, the coefficients, are they measure the marginal effects of taking account of all of the predictors of what is the impact of a given predictor, feature, explanatory variable, input. There are different names against used in the literature. You have to be careful because reading articles from one group of authors and from a different one, they can be calling the same things very different names. So you have to be careful with what they really mean by this. The forecast is obtained by setting just the error to 0, and so this gives you a forecast y hat. That's it. Okay, so this is the multiple regression. In the classical form, you estimate it by minimizing the sum of squared errors. So here you have this is the prediction. Okay, this is from the previous slide, the y hat. So you take the actual value minus your prediction. This is the error. So this is your epsilon t, and you square it, sum it, and you find such betas which minimize this. This is the idea. That's how you get the parameters of this model. And again, you can call it estimating, you can call it fitting, you can call it training, learning. I mean, there's no standard way to call it. They all mean the same. You can write it in a regression in a matrix form, which is convenient, especially if your software allows you to multiply matrices in a very efficient way. So then obtaining just the vector of parameters as a simple matrix multiplication, which can be done in milliseconds, as opposed to much more time-consuming models where you do not have this kind of solution. So this is just as simple. That's the very, very basics. Now, okay, the basic structure, which is already useful, would be a structure which is autoregressive. So you have an autoregressive part. For instance, lags from 1 to 7 days. Okay, we are building a model for our age. This is important here. So this is kind of a multivariate setting where you are just making a model for 1 hour only. Okay, we are not building all hours at the same time. It will be a different model. Then you have some calendar effects, we call them, which can be, in this case, just dummies for the days of the week, for instance. So 0, 1, it's 1 if it's a Monday, 0 if it's not a Monday, and so on. So these kind of dummies. You can have dummies for holidays also, or for some special events. I don't know, Super Bowl, World Cup. You can have this in the model. And then you can have a number, well, yeah, K, exogenous variables. And this typically for price forecasting would be the load forecast, renewable generation forecast, either separately, solar, wind, or jointly. Yeah, this would be the most common. And of course, you can add more, but you can have fuels, for instance, but it's not super, they don't improve that much. It's these variables are the most important ones. Remember that, I mean, you cannot have more dummies than categories in your setup. So you either have 7 weekly dummies and no intercept here, or you have the intercept and only 6 dummies here. Otherwise, either your software will crash, or if it's kind of built intelligent, it would take care of it itself, but you won't even notice. Maybe there will be a warning. But be careful with this. This is essentially not well-defined problem. So there'll be too many solutions possible. Okay, and of course there will be special cases. These models, even the naive model, is a super simple version of this model. So if you forget everything about apart from lag 1, you get the naive model. You can have AR7, which is just this part. If you don't use all the lags, we sometimes call it a sparse model, so a sparse AR7. You can have with exogenous variables, so with this part. You can also have a sparse ARX, which means you don't have all the lags between 1 and 7. Okay, now as I said, regression problem is essentially, you can also represent it in a neural net form. This is a graphic representation where you have the same inputs as in the previous slide, and then you have to estimate the weights, weight 1, weight 2, and so on. You don't use least squares, you can use another method to estimate it. But this is essentially the same model than the previous one. Of course, if you introduce hidden layers, this becomes nonlinear in the parameters, and then this is a more complex model. And now we'll come, I mean, also in some of the examples, we will show how such simple models, neural net models, and regression models compare. The basic differences is the linearity versus nonlinearity of the parameters, not of the variables, because here you can add, like in your paper with Tao, you were using temperature squared, temperature cube. I mean, this is a nonlinear transformation of the variable, but not of the coefficient. So the model, the linear regression model is linear in the parameters, in the betas, not in the variables themselves. Those that can be transformed. Again, OLS super fast for regression models. For neural nets, you can have different type of algorithms, all kind of numerical algorithms. Essentially fast versus slow. That's, I mean, you can have better algorithm, worse algorithm, but it will be always slower than OLS when you have just matrix multiplication. And the big difference also is that in OLS, you have a stability of parameters. I mean, it's just matrix multiplication, and every time you apply it, you get exactly the same betas. Whereas if you do it numerically, you can get different betas every time you run it because just of the different starting points in your parameter space. One solution to this would be to use ensemble averaging or committee machines, as it's called in some subdisciplines, where you essentially have you run several times the same model, you average the results. That's the idea. The number of hidden neurons, this is, again, this is the first hyperparameter we have here in this talk. The number of, so if you go back here, I mean, okay, you have the inputs. So given these inputs, how can we build a model for the output, the price for day, hour, age? Well, one of the things we have to define is how many of those nodes in the hidden layer we have. How many layers we have, what kind of activation functions, and many, many things. Now, this becomes difficult because this is something you have to somehow optimize. And of course, the different, there's no other way but cross-validation. Essentially, fit your model on some data, subsample of your data, see how it performs, and based on the results on these subsamples, you can decide on a model that you're actually going to use. So it's not, I mean, I have no idea that using for some certain data set, would the number of neurons, optimal number would be just 4? Would it be 5? Or would it be something else, some larger number? So it's essentially kind of a trial and error process to get the models working right. With the size of the ensemble, the number of runs you repeat, this is pretty clear. Typically, the more the better. And of course, there's the time. I mean, this is just, you multiply it by the number of times you have to run it. But initially, there is a huge increase in accuracy just for doing it a few times. So this is quite common, what is quite commonly done. Sometimes even it's not written explicitly, but this is what it's done in many papers where people actually run the same model a few times and average the results to get the model working. Okay, so we had the regression models, the neural nets, which can be very simple, like linear regression, which can be more complex. Then you have all the problems. You have the benefit of being it more complex in the sense representing a more complex problem, but the problem of getting it to work. It takes much more time to get it to work. A completely different class of models, quite popular in other areas, not necessarily in price forecasting, but there are a few papers. Exponential smoothing methods, where you have the forecast equation essentially is a sum of a level, of a trend, and of some seasonality component. And then you have some equations which define the evolution of those in time from time step 1 to time step 2. Again, here you don't have a closed form solution for this. You can do it numerically. You can do it, for instance, by minimizing the sum of squared errors or any other measure you want for your task. And of course, there are many different classes. If you want just an overview, you can go to Rob's and George's textbook, or you can take a deeper dive and go into more detail into those models. However, they are, let's say, simple benchmarks. I did not see any applications of more complex models, of more complex models that will be really accurate, where they would use just this exponential smoothing itself. Okay, it's time for the first break. I mean, not the break, but actually a sample code. So Ari, please come over and please explain the first snippets. So this is this one.
It's this one, yeah. Hello, everyone. So now I will briefly go through the toy models for forecasting. So everything that Rahul just told you about. So starting off, if the first thing that we need is to load some of the packages that we will use. If you are you want to go like work on it and not necessarily download the packages, you can also open it in Google Colab and then you can just run it as is. It will automatically, it has all the necessary packages there. You don't have to, yeah. Yeah, just click the link or go on the GitHub and it will just run, provided that you have a Google account, and that's it. So the first thing that it will do is load one of the data sets. So both data sets here correspond to electricity prices. They had electricity prices. And well, you can here choose between Apex and GAFCOM. So GAFCOM is from GAFCOM 2014 competition, and EPEX is the last 3 years last 2 years of data from Germany, from German day-ahead market. So if we go ahead and load this data using Pandas read CSV, we can see what we have here. So we have prices, we have load DA. So this is the day-ahead forecast of the demand. Then we have the real value of the load. We will not really use this in our applications. And then day of the week, which can be used, for example, to include these weekly dummies in regression models. And we have a date and an hour of each observation. So first, because we some of the models can take some time to calculate, we will just choose a subset of this data set for our forecasting experiment. So here we will choose a week in May of 2024. And then first, let's prepare some explanatory variables for the regression models. So here we will use these 3 lags. So this will be a 1-day lag, 2-day lag, and a weekly lag. And as you remember, these lags correspond to the same hour. So for example, to forecast for hour 12, we will use also the price from hour 12, but 1 day ago. Therefore, we have to shift by 24, 48, and 168 hours. And we will then drop some of the variables, some of the rows that are no longer needed. So if we shift the data, we will have some rows which obviously cannot have. So for the first week, we cannot have a weekly lag for our data. So we'll drop this from our data set. To start off, we will use naive forecast, because this is the one that doesn't really need any kind of training, any estimation of the parameters. So here, This is quite simple. So a function to generate this naive forecast is based on the day of the week. So if it's Tuesday to Friday, we will use the previous day. And if it's during the weekend or if it's Monday, we will take 1 week lag for that for the naive forecast. And then we apply it to our data set to generate this new column. So now our data set will also have a naive forecast column to be used later for evaluation. So now to generate, to use any of the more complicated forecasts, we need to estimate some parameters. So we'll start by selecting some calibration window. So here we use 1 year of previous data. This will correspond to taking 358 samples, basically, because of the fact that we use 7 days lags. So that's 365 minus 7. And then select explanatory variables for the model, and we will cast them to an array format. So it will be a little bit easier later to work with that. So we will use the 3 lags, so lag 1, lag 2, and lag 7, and the forecast of electricity load for that particular day and hour, and our response will be the price. So first, let's then find the index that corresponds to the first date of our forecasting experiment. So maybe, as you remember, this is the date that we set to a variable called date, and our indexes in the column correspond to day and hour. So the first hour is 0 in our data set. So this will be the starting point of our weekly forecast, of our forecasting period that corresponds to a week. So we can start with the forecasting with some more complex models than the naive one. So first, the autoregressive model with exogenous variables. Can I increase the font? It's a good question, but Alt plus works on it.
No, it doesn't.
Yeah.
Okay.
I mean, somehow yes, but on your computer, I'm not sure how to do that. Yeah, okay, so first we will prepare, so we will loop over our forecasting period. Then we prepare the training data. So we take last window of observations. So here the window is 358. So we will take this number of previous days. And we only take the data that corresponds to the same hour that we are forecasting for. And this is ensured by the fact that we are taking every 24th row from our data. So we feed our regression model. And one thing that you can that you should look out for. So depending on your software and even on the Python library, if you're using Python, linear regression will either automatically fit the intercept or the bias, but it might not do that. So then you would have to add basically a column of ones to your data set to have the to fit also the intercept. Here we don't have to do that. Scikit-learn's linear regression does fit the intercept by default. So we fit our model, and then we prepare the inputs for the next day. So this is called xnext, and then we assign the value of ARX forecast in our data set with the value of the prediction based on these inputs for the next day. So then we will basically repeat this exercise, but now with a different model. So now we will use the nonlinear autoregressive with exogenous variables using artificial neural nets. And again, we will use an implementation of the model from scikit-learn, in particular the MLP regressor. So the first lines of codes are the same. The first thing that differs is the fact that we will use a standard scaler for inputs. So we will basically remove the mean and divide by standard deviation. This is to ensure that we have a better training properties for the model. And this is a typical thing that you would do for neural networks. So we scale our data. The standard scaler fit does basically learn the mean and the standard deviation of the data, and then we transform it using a transform method. So we fit the MLP regressor. As you can see, when compared to the linear regression, we have much more arguments here for the function call, because we have to specify a lot of parameters. And so we don't really have time right now to do the hyperparameter optimization. So we just selected some parameters that work for this particular case. And also Rafał mentioned that each time you will get a different result, and that's why you will use, for example, committee machines to average the results from neural nets. So to ensure that we have the same results every time, we can just set a random state, so a seed for our random engine generator to get the same result every time. And then, so we, as before, we fit the model to our data and create these inputs for the next day. And now we have to remember that then these inputs also have to be scaled, because our model was trained for the scale data. So we need to scale it according to, with the same mean and with the same standard deviation. And then we run the prediction for these scaled inputs and assign it to our NARCS forecast column. Then we have functions for the Holt-Winters exponential smoothing model. So this is exactly corresponding to the specification that was on the slides. And now, so because of the fact that there's no closed form solution for the parameters, for the optimal parameters that minimize, for example, the mean squared error, we will have to do it like use some kind of optimization tool for this. So here is the function that that outputs the forecasts for the given the parameters of the model. So the parameters here you can see the alpha, beta, and gamma. These are stored in the first argument called params, and then S is the seasonality that we expect. We will not optimize seasonality here. We will assume that our data, we expect that the prices will exhibit like weekly seasonality. So this is something that we will just manually input. And then we will define also two additional functions which will help in our optimization. So we have loss for the Holt-Winters, which will take the forecasts from a Holt-Winters method for some specific parameters and seasonalities and observations, and return a mean squared error of these forecasts. And then calibrate method, which will find the optimal parameters. So here we will use optimize method from SciPy package, SciPy library, which will minimize the loss for Holt-Winters, so the mean squared error of the forecasts. So actually, because this is in sample, this is just a sum of squared residuals. And here are the initial guess for the parameters, and bounds correspond to with the parameter space that we will search. So we want our coefficients alpha, beta, and gamma to be between 0 and 1, and this is what we specify here. And we return the optimal parameters, so the parameters that will minimize this sum of residual squares, squared residuals, yeah. And then, so finally, we can generate the forecast using Holt-Winters model. So as I said, we set seasonality to 7 days. And once again, we iterate over our forecasting period and find optimal parameters for each window, calibration window, and then assign the forecast for the specific day to our data. Then we will remove the days without forecast. So you can see that now we indeed just have a week of data. So 168 hours in total. And we can finally plot the time series of our prices along with the generated forecasts. So there's a lot going on this plot. So one thing that you can easily notice is the naive forecast, that it is just indeed like shifted, a shifted time series of prices. So for example, this part here exactly corresponds to what we had 24 hours before. So here you can see this can stand out, but this corresponds to beginning of Sunday. and this is where the value of 1 week ago was taken. So this is not present in this series. That's why it's a little bit stands out from this series. So let's maybe take a look at how error measures look for our forecasting methods on this particular week. So here we will calculate the root mean squared error, mean absolute error. So this is, you can use just existing scikit-learn's methods for that. And the relative MAE. So relative MAE will be the mean absolute error of our forecast with respect to the mean absolute error of the naive forecast. So then we can actually check if we beat the naive. So as Rafał said, if we don't, then we didn't really do a good job. So as you can see, in the ARX model works best in terms of both root mean squared error and mean absolute error. You can see that the NARX model is performing quite poorly. So one important thing is that we just didn't optimize any hyperparameters. We just put something that worked, and this is a very short forecasting window. So it's important to also keep that in mind. But in terms of relative MAE, we were able to, all of these methods beat the naive, and quite significantly, I'd say. And so this is everything for the toy models. If you have any questions, I don't know if there's time for. Yeah, great, sure.
So let me just finish maybe this. Okay, I was thinking whether this. No, it doesn't work this way. Okay. Okay, so if you have questions regarding the codes themselves and during the coffee breaks, ask Arek for the details. I'm not a Python programmer. I myself, I prefer MATLAB. I grew up with MATLAB. I'm still using it. But if I have to, I do it. I tell chat to convert my MATLAB codes to Python, and then struggle for the next 2 or 3 days to get them working. But yeah, that's that's life. Anyway, okay. The last model I have in this toy model section is. It's a toy supply stack model. So it's a completely different model from the previous ones. The previous ones were essentially looking at the prices only. Now we take we look mainly at the fundamentals. We don't care about the prices so much here. So it's in the, if you go into one of the earlier slides where you have this classification, the taxonomy of different price forecasting models, it's from the class of parsimonious. Oops, okay, and lost track of it. Let me just connect for a while. So it's from the class of parsimonious structural models. So it's some fundamentals are in there, but it's very simple. Now the assumptions are that this is an island grid. So okay, we have no interconnections to it. So that's for simplicity. We have a power park which is composed of J units. Every unit is characterized by its installed capacity and marginal cost. So how much producing an additional megawatt hour by generated J. This is an illustrated table with all the whole generation park, ordered from the cheapest, so with the marginal cost here, to the most expensive plants, and this is roughly corresponds to kind of a miniature to Germany in 2018. That's what this is the work with Florian Thiel and an example we have developed. So we have 10 different types of generators. Some of them are a few times here. Now the merit order curve is given. So the merit order curve at X, where X is some volume that is needed to be generated, the demand that has to match the demand, is just we take essentially this MC. Indexed by the J, which is the last unit that is needed to generate enough electricity. So here's the cumulative capacity. Essentially, we can look how much we need to generate, and we stop here. Let's say this is the last unit here. Then the price will be set by the marginal price of this unit. If you plot it, we have this is the generation stack with some colors indicating the different types of generators. Now, if you have a prediction, I mean, now what you need is a prediction of demand. So what is the demand and the intersection of the demand. And if you have this supply stack correctly representing what is really available in the market, then you get a kind of a fundamental price. What should be the fundamental price for? So the intersection of these two give you the fundamental price. Now, the biggest issue here is getting the supply stack right. So for us academics, there's no way we can get it right. But some of the companies we've been working together with, they have access to such information and can pretty accurately have for each hour, they know what will be the generation stack. So this is a completely different way to approach the problem of forecasting prices. But from this type of models, you get the fundamental price of electricity, whereas the others also include the gaming, the trading activities. So that's a different approach. And just to give you a sample from how this supply stack model works here, well, it works really bad. So this is this kind of rotated squares. They are from the supply stack model. The supply stack apparently is too simple, doesn't catch, well, it kind of catches the dynamics, but not really well. Okay, so you need to do a lot more detailed information about the supply stack to really get it working. The other two, the green one is the naive again, so it just matches the previous day here. Whereas the squares, the purple squares here, is an expert model. This is one of the names used in the literature for autoregressive type of models. So, well, this is the best out of the three here, but it's just to show you that what kind of different results you can get with different types of models. If you play around with the codes that Arek was showing, actually changing the weeks or maybe some parameters of the neural net, you see also how the results can change for the neural net really drastically from if you change some of the parameters. Okay, this is the middle of the talk. So maybe Tao, we take some questions now. If anyone has a question, then maybe there are no questions. That's another option.
Any questions? Any questions?
I guess it's too simplified one. I wasn't sure.
Load forecasting, and I was wondering in your experience, looks like a very similar process to price forecasting. So what do you find are the major differences?
Okay, I'm not sure I have the plot here. Okay, major differences, much higher variability. In the load forecast, I mean the load process or consumption demand, it's more or less, okay, you have the fluctuations, the daily, the weekly, at some high level, whereas the prices, they can be negative. A price can be negative if you have a fossil fuel generator which doesn't want to, I mean, turning it on and off is a complex process, technologically and time consuming. So sometimes for a few hours, it's better to pay someone to take electricity from me than to turn off and turn on later on the boilers. So you have with renewables, you have a lot of negative prices nowadays in Europe. You have much higher spikes, and this is because of the highly nonlinear structure of the supply and demand curves. So when they intersect in the upper region, even a small change can just shoot the price 2 times, 3 times, 10 times. In some markets, like the Australian market, there the limit, I think current one is $12,000, 12.5 or something, and you can have like from hour to hour, it goes from 100 to 10,000. So it's really huge differences. So in this sense, it's much more volatile, much more sensitive to some changes. So one of the most important exogenous variables is load forecast, because if it tells you a lot what is going to happen. The second one is the generation from renewables, because then the residual of the difference between the two gives you the most important information about the prices, what is going to happen to the prices. Because if you have a lot of renewables, the fossil fuels, the fossil generators, they will have to lower the prices or just pay someone to take the electricity from you. So the prices will drop. But if the demand is high at the same time, then this won't happen because every generation is needed. So it really depends on the consumption, the load at the given moment, and the generation from renewables. Okay.
Let me add something. So regarding the difference between load forecast and price forecast, so there was a fact. So in 2014, when we had the competition, we had 4 tracks: load, price, wind, and solar. So So Rafael's team ranked #1 in price.
Number 2, actually. The EDF I think was number 2, number 1. Okay, anyway, that's my. I was not okay. It was my colleagues, younger colleagues. So
So, price tag, and there was a team that ranked #2 across the board. So I mean, ranked #2 in both in price, wind and solar. Or maybe #3 in price and #2 in wind and solar. So they use the same methodology, basically pretty much the same software, the same method for all low price wind and solar, but they only ranked #2 or maybe 3 in those 3 tags, and they were not highly ranked in low. So that tells you the difference. The same method probably work on the other 3 tags, but not on low. And the lady just sitting right here, Rain, she was I think top 3 or something. Before one of the winners in the low test, so super competitive, and she was on my TV and only spending 10 minutes a day, a week to submit the answers. All the other ones were teams, like EDF, they have 4 people. Over there, we have a lady in maternity leave and trying to finish her PhD.
Thank you very much for the part of the session. Very important. My question relates to the use of exogenous information in the price forecasting. So I do work in wind energy forecasting, and we have a good source of exogenous information, which is numerical weather forecasts. But with electric price forecasting, you have exogenous information that is difficult to predict in the first place, like renewable generation and things like that. So how do you see this as a barrier to get good electricity price forecast, the propagation of errors from the input sources? Yeah.
okay, well, most of the models somehow adapt this poor quality of the forecast, but actually what we often do, most of our models we run on publicly available forecasts for the load for the load and for the renewable generation, meaning they are not very good. I mean, these are the TSOs that are issuing those information. There's a platform in Europe, NSOE, which provides this to everyone with some time lag, but of course, if you are a member of it, you get the information earlier on, so it's useful. But these predictions by the TSOs are not really great quality. So what we actually do, we improve them. First, run models on the load forecast and on the renewable generation forecast, and plug those into our models. So this helps a lot. And I'll talk tomorrow about an interesting concept where we're actually plugging in probabilistic forecasts of their fundamentals, really improves the point forecast of prices. So so combining different concepts of price forecasting or, well, energy forecasting, we can do really better. So I'll show something like this tomorrow. Okay.
Any other questions? Okay.
I work for forecasting too, but my question is, so you mentioned about the baseline forecast, which is night forecast, right? Now, in terms of when you have exogenous variable, what would you suggest to have a baseline forecast? Can linear regression be used as a baseline forecast, or
You mean a baseline, baseline forecast for load forecast or?
yeah, baseline method basically.
Okay, this naive naive model which I mentioned is just the simplest possible thing. I mean, you can just take the previous day's load. I mean, in load, you don't have this. I mean, you have some effects, but you can use even the same naive forecast as a really simple benchmark. If you really want to benchmark against the model I've shown, so this one would be really a benchmark that you should test against. Okay, as you will see later on, I mean, as we move on in time and improve our models, we choose better benchmarks. So this is really simple. This used to be the benchmark. Nowadays, we use lasso estimated autoregressive models, so much bigger models as benchmarks. So it changes over time. But I'm kind of starting from the first simple models. This is what used to be the really benchmark. And if you can't beat that, then go home. Okay, that's it. That's the message.